sklearn Gaussian process kernels exp sine squared. Description: the exp sine squared kernel is a stationary kernel that is suitable for modeling data with periodic patterns. It combines a periodic component, represented by a sine function, with an exponential decay component, resulting in a kernel that oscillates with a period of length period and decays with a characteristic length scale of length scale. The kernel is defined as kx1, x2 xp x1 x22 to length scale 2 sin 2 pi x1 x2 period 2, where x1 and x2 are two input points. Length scale is the length scale of the exponential decay, and period is the period of the sine function. Inputs: x1 the first input point, a one-dimensional array or scalar. x2 the second input point, a one-dimensional array or scalar. Outputs: k the kernel value between the two input points, a scalar. Steps: calculate the squared distance between the two input points x1 x22. Divide the squared distance by twice the squared length scale x1 x22 to length scale 2. Take the exponential of the result, express x1 x22 to length scale 2. Calculate the sine of twice pi times the difference between the input points divided by k. Period sin 2 pi x1 x2 period. Square the sine value sin 2 pi x1 x2 period 2. Multiply the exponential value and the squared sine value to obtain the kernel value, express x1 x22 to length scale 2 sin 2 pi x1 x2 period 2. Metrics: the exp sine squared kernel does not directly provide metrics, but it can be used in conjunction with a Gaussian process to estimate the underlying function and its uncertainty. Metrics such as mean squared error MSE or root mean squared error RMSE can be used to evaluate the model's performance on a test set. Visualization plots: the kernel function can be visualized by plotting its value for different pairs of input points. This can help to understand the shape of the kernel and how it captures the periodic nature of the data. The Gaussian process itself can be visualized by plotting its predicted mean and variance for different input points. This can provide insights into the model's uncertainty and how it interpolates between observed data points. Fine-tune parameters. Length scale controls the length scale of the exponential decay. A larger length scale corresponds to a slower decay, meaning that the kernel will be more correlated for points that are further apart. Period controls the period of the sine function. A larger period corresponds to a longer wavelength. Uncertainty methods. The exp sine squared kernel can be used in conjunction with a Gaussian process to estimate the uncertainty of the predicted function. The Gaussian process provides a distribution over possible functions that are consistent with the observed data, and the uncertainty is captured by the variance of this distribution. Challenges and fixes. Challenge 1: overfitting to the data. Sample use case that resulted in challenge 1: if the length scale and period parameters are not chosen appropriately, the model may overfit to the training data and fail to generalize well to new data. Fixes to challenge 1. Use cross-validation to tune the hyperparameters of the kernel. Consider using a regularization term in the Gaussian process to penalize complex models and prevent overfitting. Challenge 2: choosing the appropriate period. Sample use case that resulted in challenge 2: if the period of the sine function is not correctly chosen, the model may not capture the periodicity in the data. Fixes to challenge 2. Perform a Fourier analysis of the data to estimate the dominant frequency and use that as the period. Explore different values of the period and select the one that leads to the best model performance.